Hello everyone and welcome back to tutorial 3 in our MSP neural networks series. Last time, as if you'll remember, we built this neuron abstraction here where we've got the neuron and the subneuron section going into a polytilde so we can have a dynamic number of inputs. This time we are going to look at the next article that this bloke wrote about building neural networks in Python, where we make a multi-layered neural network. So we actually have a network of neurons connected to each other. And the reason we want to do this is what we're dealing with this time is we've still got 3 inputs and 1 output, but if you have a look, there's no direct relationship between, say, one of the inputs is correct and the other 2 are incorrect. In this case, this training set forms what's known as an XOR gate. Now the third input is irrelevant. That's again another little test for the network to work out that that is irrelevant. But the first 2 inputs form what's known as an XOR gate. Now if you're not familiar with logic gates, they're basically a series of things where you can have the inputs either on or off, and depending on which gate you're using, the output will then also be on or off. Like you can have an AND gate where both of the inputs have to be 1 for the output to be 1. But in this case, the XOR gate means that if both of the inputs are the same, the output will be 0, so off. But if both of the inputs are different, then it will be 1. So you can see here we've got 2 zeros, so it's a 0 and a 1, so it's 1, a 1 and a 0, so it's 1, and then a 1 and a 1, so it's 0. So that's what an XOR gate is. And the reason we can't just get our individual neuron to work this out is because the neuron itself only finds how much it should weight each individual input against the value of the output. But what we're doing here is trying to work out the relationships between the inputs and how that affects the output. So if we scroll down to this diagram here, he shows how our network actually looks if we kind of try to visualize it like this. Now he's got the inputs here as displayed as if they're neurons themselves, and that's the regular sort of parlance for how you display a neural network when you make a diagram of it. In our case, obviously, we don't have neurons for the inputs themselves, and in general, you don't. They're just inputs. It's just easier to visually express them like this. In this case, it's this set of objects here which form our inputs, all of them in one thing that then go out to all of the next neurons in the next layer. So that's fine, but you'll see here we have these 2 layers. The last layer in any neural network will be an output, and this output neuron works in a very similar way to our previous regular neuron. Actually, there's not too much we need to change about that. But then all the neurons between the inputs and the output are known as hidden neurons, so it'll be a layer of hidden neurons. And so these will then take each of the inputs, determine their own weights for them, and then the output neuron will be determining its own weight of those hidden neurons to find the relationship between the inputs to then determine what the output should be. This is actually my second attempt at recording this, which is why it's being uploaded a little bit later than normal. And that's because I recorded for about 40 minutes going through rebuilding all the objects with you again. And then I realised after I'd finished all that that the microphone in QuickTime Player was set to not my inbuilt microphone in my laptop, so there was no sound, so that was fun. And partly because of that, and also partly because if you've followed me this far, you probably don't need to be handheld walk through every single step of rebuilding the neurons. So what I'm going to do this time instead is go straight to the final test, as it were. So we get the Net Xor Gate. This will be what we'll end up with. So what we've done is we've taken the neuron and the subneuron part and we've rebuilt them as output and hidden neurons. So if we go into the output neuron first, let's go through into the sub-output neuron. So just take what we did before, save it as a new file as sub-output neuron. Now as you can see, most of it is practically the same. The way that we work out the adjustment is still exactly the same. We do the error, which is the training output, minus the neuron output to get the error, multiply that by the sigmoid curve gradient, which, if you remember, is the neuron output times 1 minus the neuron output, and then we multiply all of that by the input to get our adjustment to each of the weights. Now you'll see I've done this slightly differently here. We've broken up this expression object so that the input isn't multiplied at that stage, it's multiplied afterwards. Now the reason we want to do this is to do with how the error is worked out for the hidden neurons. So obviously in this case it's still exactly the same, but for the hidden neurons, if we go to his Python code here in the article, you can see, yeah, we've got layer 2, which is the output layer. Adjustment is, yeah, the output from layer 1 times the layer 2 delta, which is the change in layer 2, which is the layer 2 error times the sigmoid curve gradient. So that's fine, that's what we know. But for the layer 1 adjustment, we have the training set inputs, so that's fine, times the layer 1 delta, which again is the layer 1 error times the sigmoid curve gradient. But to get the layer 1 error, we can't use the training set outputs because that's not what the hidden neuron is trying to work out. What we need to use instead is the layer 2 delta itself, which is the error times the sigmoid curve gradient, and then multiply that by each of the relevant weights in layer 2. So if you look again at these, each of these lines between each of the neurons, you can think of that being the weight that we have determined. So each of these weights will be within our output neuron. So what we want to do is find the error in output 2, in the output neuron, layer 2, times its sigmoid curve gradient, and then times that by each of the individual weights and send the appropriate one out back to the appropriate hidden neuron, and then multiply that by the hidden neuron's sigmoid curve gradient, and then multiply that by the input, and that becomes the adjustment for layer 1. So what we've had to do here, that's why we've split this up, because we want to take the error times the sigmoid curve gradient out, multiply that by the weight, and then send that out of a new outlet there. And then obviously it carries on here to be multiplied by the input to get our adjustment for the output neuron weight itself. So you can pretty much see how that works. And then when we go back to the output neuron itself, which I've named neuron output as opposed to output neuron, that's just the way I've done it. You can do it however you like. We've built a new ZL group object here, which if I unlock this, you'll see that is not 4, it is #1, because we want that to be the argument again, into a new list funnel object and out of there. And we've moved the one that we built for the weights over here. And remember to reconnect that to the third outlet, which will be to display the weights, whereas this will be connected to the second outlet, which will be the weighted errors coming out into there, which will then be grouped depending on how many weights we have, how many inputs we have, and sent out as indexed floats. You can see there, I've named that outlet weighted error out indexed floats. And we've done a little bit of changing up here. We've made a new inlet that is expecting to have the training output in, because the input is just going to be the outputs from the previous layer. Now obviously those are not going to include the training set output, so we've got rid of all that ZL Eccles stuff that we had here before and just separated them entirely, so that the inputs from the hidden layer come in and go to that input 2 as they were going to before, but then instead we've got the training set output coming in to our input 4 there. But other than that, that's basically the same. And if we have a look at the hidden neuron, it's quite similar again, but a little bit different. So what we've done here is we've got exactly the same thing, but instead of finding the error manually by taking the training set output and minusing the neuron output, we've got our next layer weighted error in that will be coming from the output neuron, and that just needs to be multiplied by the sigmoid curve gradient. But this is going to be, the reason I've changed the inlets around is depending on which one is hot and cold. We want the hot one, the hot one's obviously going to trigger it, So we'll have the output coming in first, and then the last thing that comes in will be the next layer weighted error in. So we want that to be the thing that's actually triggering the calculation. So that's why we've changed this around slightly. So now the sigmoid curve gradient is 1 minus $f2 times $f2, and then times the next layer weighted error in, which is $f1. So that triggers that. And we have to build exactly the same thing here to get our weighted error out for this layer, because in this case that we've got here, we've only got one hidden layer, because that's all we need to determine an XOR gate. It's not that complicated. But say we did have a much more complicated neural network with multiple hidden layers to determine something like I mentioned in the very first tutorial, like a cat picture. So looking at, potentially thousands of pixels. We would need more than one layer there. So the way it works is it works exactly the same way. You just have to take the delta of the previous layer, times that by the weight of that layer, and then send that out to the layer. Sorry, not the previous layer, the next layer. So you know what I mean here. So for layer 1, we take the layer 2 delta, and it says layer 1 and 2 in this case because that's what we've got, but essentially it is whatever layer you've got, you take the next layer's delta, which is the error, times the sigmoid curve gradient, and then multiply that by the individual weight, and then multiply that by the sigmoid curve gradient of this layer. If that makes sense, that is what we need to do here, so that we can then connect that to a previous layer of hidden neurons. So that is why we've built that like that. And the changes to the hidden neuron are virtually identical again, it's just we don't have an extra inlet for the training output. Instead, we have an extra inlet here for the next layer weighted error in. Now, obviously they're going to come out of the output neuron indexed, but we don't need to worry about that right now because we're going to change that outside of these actual neuron abstractions. We're going to send them to the right neurons outside of this. So essentially this is just going to be expecting a float, not an indexed float. So then we want to target 0, so it goes to all of the iterations of this polytilde and then send it in to inlet 4, which is expecting the next layer weighted error in. Other than that, we change this so that it's exactly the same. It's not expecting to have the training output anymore, it's just expecting the inputs. And again, we've got our second outlet, which is going to go into a new ZL group #1 and list funnel out of there, moving the weights ones over there. Now you might notice that I've got this sigmoid function object instead of the little expression object that we used before. The reason I've done this, and inside it's exactly the same, but the reason I've done this is when we get further down the line to making more complex neural networks, we won't just want to be using this sigmoid function all the time. This is what's known as an activation function, and if you remember, it's squashing our output within a particular range, in this case between 0 and 1. But we don't always want that to be between 0 and 1. Sometimes we might want it to be between -1 and 1, or we might want it to just not go below 0, that kind of thing. So at a later date in another tutorial, I'll be expanding on this sigmoid function object and putting in multiple activation functions that we can then choose between. But for now you can just leave it with the expression object there as we had before. So that's fine. So that's both our hidden and output neurons, and this will look fairly familiar to you. It's exactly the same setup, just with a different set of training data that matches this set here. You can program that in by yourself, you can see that's there. Obviously I've connected a bang to the first inlet of each of the hidden and output neurons because that will be resetting the weights. We've attached a toggle to the third inlets of hidden neurons and the fourth inlet of the output neuron to turn training mode on or off. We've got a ZL equals 1 object which is taking our data here and shaving off the last value, which will be the output, the training output, sending that into the output neuron and sending the rest of it into all of the hidden neurons here, into the second inlet there. And for the next ones that we're going to be testing it with here, I've added the output there. It doesn't have to be the correct output, because when we test these, we're going to be turning training mode off, so it won't affect the adjustment or anything. I've just put those there just to show what we are expecting anyway. And then we have to group together the outputs from the hidden neurons. So we've got 4 of them. We'll be getting a float out of each of those, group them together in sets of 4, which will then be the inputs for the output neuron that it's taking. And then the final thing we do is we send the weighted error out to this spray object. Now, spray object expects to have indexed items coming in, so an integer or a float with a 0 or a 1 or a 2 or a 3, etc. in front of it. And when it takes those, you can see it's expecting the outlet number followed by the data. So here, anything that's tagged with 0 at the beginning will come out of the first outlet, and then the second, third and fourth outlets, etc. it will come in order. Now I need to delete these and redo them, because what I made the mistake first of all of connecting these in the wrong order. Because if you remember, Max works right to left unless you find a way to specify that it doesn't, but in general it will send data in a right to left order. So the information that's coming out of ZL Eccles will be going to this neuron first, and then that, then that, then that. So the ZL group, the list of floats that we'll get will be this output first, then this, then this, then this. And likewise, the weighted errors coming out of the output neuron will be weighted in terms of this one, this one, this one, this one, rather than left to right. Now initially when I was testing this, I completely forgot that, and I just connected these up left to right. And bizarrely, it still worked. And I don't know why. So if someone can work that out and post your ideas as to why that might have worked, that would be awesome. But what we're supposed to do is connect them right to left. So if you connect each of the outlets here with the appropriate inlet on the hidden neurons, we'll do Command-Shift-E. Oh, isn't that nice? Just makes them all perfect. And that is our neural network. So what I'm going to do now, we'll see if this happens this time. It might not, but we'll change this to 60,000 instead of 10,000, as he specifies here in the code here. Do it 60,000 times because it's a more complicated thing. But as I was saying, when I was testing this again, I had a bit of trouble at first, because a lot of the time this network gets it right and gets the right answer, but sometimes it didn't. It got it wrong. And I was completely flummoxed by this until I tried adding more hidden neurons. I added 4 more to get 8, and then it got it right every single time. And the reason I think this is I don't think it's a problem with the training data as we saw with the previous set, that it was less than optimal. What I think it is what a neural network is essentially trying to do is minimize its error always, so that we can get as close to the correct value as possible. And now if we've got a single neuron, you can visualize that error as a kind of as a hill, and we're trying to get to the bottom of that hill, and that's where the whole sigmoid curve gradient comes in, because we know sort of how steep the hill is, so we know whether we're getting close to the bottom or the top. So that's fairly easy to work out. You can see where the bottom of the hill is, and you can get to the bottom of it. But if you think of it like you're in a mountain range rather than just on one hill, you can get to the bottom of a valley in that mountain range and look around you and think, okay, well, I'm at the lowest point here, so I'm in the right place. But what you might not know is that over the next mountain there might be another valley with an even lower point. And obviously what we're trying to do here, when we've got multiple layers and multiple sort of layers of complexity, is we're trying to get to the lowest point in the entire mountain range. And when you get incredibly complex neural networks, it is a multi-dimensional mountain range. It's not just 3-dimensional, n-dimensional. It's just ridiculous. So if you have more neurons, you're essentially giving yourself more vantage points from which to find the lowest possible place in the range, as it were. You're giving yourself more eyes, more locations to search. And I think that's the reason that it works. Now, I don't know if that's going to work the same with the Python code, because he only shows one situation here where he's considered the new situation, and that's correct, so therefore the whole thing works. I don't know if this is something where Max is just not able to compute it as accurately as Python can. I don't know. But so let's try this just to see if this works. So yeah, we make sure training mode is on, we bang it, and then we get it going. Now you'll see here, yeah, there we go, we start to beach ball. But that's fine. The reason is, obviously, we're doing a lot more calculations than we were with the previous one, where we just had a set of 4 sets of data rather, and doing it 10,000 times. Now this shouldn't take too long, it only takes around 30 to 45 seconds on average when I've been testing it. There we go. So let's turn training mode off and test this. So the output when I click this should be 0. That's right. That should be 1. Okay, so it's got it right this time. Now I'm just going to test it again, rebang everything. I'm going to do it until, just to prove that I'm not going mad, I'm going to do it until it gets it wrong. Now you can probably already tell that you know, it's taking a bit longer to do these computations. It's not very long, it's fine, we don't need to worry so much about it at this stage. But you might already be able to see that when we get a much more complex neural network with much more, loads more inputs and different things. Here we go. Right, I'll get to that in a second. But when we get to more complex neural networks that are going through maybe 100,000 iterations or more, which I have actually tested with a multi-layer neural network, in which case it took about 15 minutes to stop beach balling and come out with the correct output. And that's a problem, because when we start to get to these kind of neural networks that might be able to analyze sound to generate new pieces, you might be having to leave it for hours or days potentially, which just isn't realistic. Now that's partly because of just the way that Max works. Max, as anyone who does programming will tell you, Max is not a particularly well optimized program in a lot of ways, but there is a new sort of set of, well, a new way of working in Max that's come out reasonably recently, known as Gen. And I don't know very much about it, but from what I understand, you can rebuild a lot of patching in Gen, and it functions a bit more like Python, or like a regular coding environment where everything sort of happens more or less instantly, which will help a lot from a computational standpoint. So at some point in the future, I'm going to look into Gen. I'm going to look at maybe rebuilding this all in Gen and see how much it helps with the computation time. But going back to this, you can see here, if we do this one here, the output should be 1. Yeah, that's right. The output of this should be 1. That's right. Output of this should be 0. That's right. But when we click this, the output of this, because the first two are the same, should be 0, and it's not. So the neural net has failed, as I predicted, as I said it would. But if I open up a slightly newer one that I did, Neural Net Xor Gate 3, I did several tests, where you can see here now we've got 8 neurons instead, and we've had to change the argument of the output neuron to 8 because it's expecting 8 inputs, and likewise the ZL group 8 and the spray 8 object. And yes, I've got those in the right order. Good. Now you can see I've attached bangs to the last inlet of each of those so that we can print all of the weights, as we should be able to. Let's just test that. Bang all of the weights, bang that, yeah, perfect. So those are all the weights coming out. It'll be right to left, or however I programmed it, with the output neuron at the bottom. Yeah, 1, 2, 3, 4, 5, 6, 7, 8. So those are the initial weights for all of them. So let's turn training mode on, make sure we have the right set of training data, and bang that. So now it should take a similar amount of time, maybe a little bit longer, because obviously there's more neurons and more data being sent to the spray object as well. But what should happen is this should come out with the correct answer, the correct weightings all the time, essentially. So we'll wait until this finishes beach balling, which it should do any second now, and then test to see if that is correct. Okay, you can see I've added a ZL clear object to the ZL group as well, just so that we can rejig that if necessary if we accidentally send out the wrong number of neurons into that, which does happen. It happened to me several times, and it, as I said in the last tutorial, kind of knacks up what you're doing, which is not fun. Here we go. Come on. Come on. Okay, well I'll use, oh there we go, okay that's fine. So let's turn the training mode off. This, yep, we've got close to 0. This, we've got close to 1, close to 1, close to 0. Perfect, and you can test this for yourselves. I'll be uploading a download link to it as always. But you can test it for yourselves, but from what testing I've done, and I've done it quite a few times, it always comes out with the correct output now. So that is our actual neural network as opposed to just a single neuron. So that's great. That's the basis for any more work in neural networks that we want to do. In the next tutorial, what I'll be doing is basically doing what I did the last time, but on a higher level. I'll be abstracting these neurons again, but abstracting them as layers, so that rather than having to manually put in all of these neurons and then connecting everything up to them manually, we can just type hidden layer and then give an argument of how many neurons we want, and then another argument which specifies how many inlets those neurons are going to have, and likewise with an output layer. Because even though in this case we've just got the one output neuron, depending on what you're trying to determine, you might want several output neurons that are all expecting to find different outputs. So that's great. That's what we're going to do next time. For now, this has been the third tutorial. Hope you all enjoyed. Thank you very much for watching, and we'll see you next time.